if f is continuous, why is this string of funny looking garbage true? Okay, so to answer the question, we first have to understand what is the idea of this squiggly line over here. Now, for those of you who know, can recognize this is integration. But what is the idea of integration? Integration is so for example, if I were to have a curve something like this, suppose for f, and this is my x-axis, this is my y. If I have 0 and 1, 0 in the lower and 1 in the upper, I'm going to look at the x here, which is 0, and the x here, which is 1. I'm going to shake the area underneath, all the way to the x-axis. Okay? So this area is what I'm looking for. When I integrate f with respect to 0 and 1, the answer that I'm going to get is basically this area over here. So we want to ask ourselves, okay, then what is this left-hand side over here? Well, if you take a good long look, which even so you may not get it. I certainly wouldn't have gotten it. This is actually the creation of the idea behind integration by very clever mathematicians in the past. Okay, and the idea goes like this. Well, let's zoom in, I suppose. Let's zoom in here. Let's say this is the curve. It's from 0 to 1. Well, for math in the past, if you don't have, suppose integration is not created, what could you do? Well, you would say to yourself, well, I don't know the formula of funny shapes like this, but I do know the formula of a rectangle. Right, yeah, that one I do know. Right, length times breadth. Or base times height, whatever you want to call it. Right? Then they say, okay, well, I know that I like to eat kueh lapis. So what I'm going to do is I'm going to try to draw some kueh lapis slices here. And for those of you who don't know, kueh lapis is a cake. Singapore delicacy. Okay, I'm going to cut up the x-axis into equivalent chunks, suppose. Yeah, this point included. Okay, and at any time it is the point on the curve, well, I'm just going to draw a line parallel to the x-axis, and there I have for myself a rectangle, another rectangle, so on and so forth. Okay, and if I were to sum up all the areas of these rectangles, wouldn't that be an area close to the area under the graph? But then you say, hold on, Mr. Pang, but then these empty bits over here, it's not considered your area, it's less than the correct answer. I say, and that's true. So how about for our kueh lapis curve, we introduce more layers, cut it thinner. So let's say I do it thinner. Okay, I'm gonna have many slices and I'm too lazy to draw. Okay, when I get the area of all these rectangles here, you will realize that the area that is left out gets smaller. So that's a good idea. Making the slices thinner reduces the error, and the error is the discrepancy between what we got and the true area under the graph. So I'm gonna have a very good idea. Make these rectangles so thin that they are literally lines. Okay, you can't see this, but it's a rectangle. I'm drawing many rectangles. They are so thin, so close to each other. The error term, when you zoom in, you probably have to zoom in 1,000 times, 10,000 times before you can notice any discrepancy, right? And when it's so thin, what am I gonna do? Make it even thinner. And then you're gonna say, Mr. Pang, how thin can we go? I said, never stop. Keep getting thinner. Thinner and thinner and thinner. And that's the idea of infinity. Okay, again, infinity is not a number. Infinity is a concept. Alright, what is a number? 9, pi, these are numbers. Okay, infinity just means keep getting bigger. and then keep getting bigger, and then keep getting bigger, and don't stop. So what number is infinity? Nonsense, no such thing. It just keeps getting bigger and bigger. Okay, sort of like the universe, so to speak. Okay, that's infinity here. So I want these rectangles here. Okay, if I could even zoom in until you see a rectangle rather than a line, which is it still is a rectangle, what you're gonna see is this width over here is getting very close to 0, but never actually 0. Okay, how do we achieve that? By cutting more and more pieces. Right? How to do this? We want to cut more pieces. How much more? Infinitely more. Never stop. Get thinner and thinner. Okay, so if I were to say from 0 to 1, cut n pieces. 2, 3, 4, 5, 6, 7. In this case, cut 7 pieces. What is the width of one of this rectangle? Well, there's 7 pieces, right? And the total length is 1 unit, so 1 over 7. Suppose that in the bottom case over here, I let n equals to 20, cut 20 pieces. Then each width would be 1 over 20. Ah, yes. You see that the width is getting smaller. Very good. So how many rectangles must I cut to make the width very, very close to 0? And even closer, you need to cut n tends to infinity pieces. Okay, very good. So we have settled the n over here. We know that the base is, okay, let me draw the rectangle proper. The base is 1 over n. And what is the height? Well, remember that we took whatever point here and substituted in, right? Okay, we could use the left or the right. Okay, in this case, I will choose the right. So here, for example, here. Okay, look at my very first triangle. This is the origin. Okay, and then this is 1 over n. The next one will be 2 over n. That's for later. So I'm going to take this point. I'm going to substitute in the curve over here. And we know that the curve is y equals to function of x. Now in this case, I'm substituting x equals to 1 over n. So this is just f1 over n. Correct? And then what will be the next rectangle? I'm going to take this value and substitute it in. Okay, in this case, we want to generalize f, the function. So there is no real equation that we're substituting in. We're just going to leave them as such. Okay, that means that for whatever piece that I'm taking, let's say this is piece number n, and then n could be the first piece, second piece, blah blah blah, all the way to the nth piece, right? All the way to the nth piece. Okay, let's not confuse ourselves. Let's say piece r. Okay, so the base is 1 over n, and the height is f r over n. So this is the total area. Now, remember that I told you if we can make this, if you can make n bigger and bigger and even bigger, then the total area would tend towards the area under the curve. So the a I have here, the summation of a, gets very, very close to integrate 0, 1 fx. Gets very, very close when n tends to infinity. So how do we write n tends to infinity in the same equation? Well, if it were to be 2 lines, I can just write n tends to infinity, and then fx tends to copy paste all this, copy paste. Well, but if we want to be elegant, okay, we want it to be in 1 line, then this is just, you know, the math lingo, how we're going to write it. I'm going to say this. Okay, this allows us to write it in 1 line. This is talking about limits. And then just copy and paste everything. Okay, and you see that what we have here is very, very similar to what we have there. Okay? So basically the whole grandmother story that I've told you, you have to try to explain it in a short para to them. This was an A-level question. I understand the marks is not all that high. Okay? Again, you are not required to make this grand explanation, but the key ideas you have to hit is we are cutting on the x-axis n many parts so that we have n rectangles, and each of these rectangle has the base of 1 over n and the height over f r over n. Okay, where r is dependent on the number of which piece number the rectangle is. Is it the first piece, second piece, so on and so forth. And then when n tends to infinity, it's the last point, n tends to infinity, the sum of all this area of the rectangles tends towards what we wanted, which is the integration. Then therefore we can have this formula over here. Okay, of course the lesser marks there are, the lesser you have to show, but you have to always capture the idea of the concept. Okay, so cut into pieces, each rectangle has this dimension, and then n tends to infinity, you get the formula. Okay, I hope this explains.